Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. In the Cook Inlet Basin of Alaska, there are two interfingering neogene formations with fluvial sandstones and shales. Deposited in similar environments and with similar burial histories, one has produced high-quality hydrocarbon reservoirs, the other poor-quality reservoirs. The formations are the Stirling and the Beluga. The Stirling contains the giant Kenai gas field, the Beluga relatively few small fields. Despite the obvious similarities, the two sandstone reservoirs followed very different diagenetic pathways. But why?
Answering that question requires a solid understanding of both the depositional factors and the diagenetic factors that affect sandstone porosity and permeability, factors that in turn affect the location and distribution of reservoir quality sandstones. Welcome to GL 505, Porosity Evolution of Sandstone Reservoirs. In this module, we'll be examining the factors that affect sandstone porosity during deposition and throughout the burial process. This module is designed to introduce you to the important, though sometimes complex, diagenetic processes through which porosity develops and evolves in response to changing physical and chemical conditions. You'll also see how understanding this evolution is important in the search for new hydrocarbon reservoirs and in optimizing existing production. This video program is divided into 4 units. The first unit covers factors that control primary porosity. Unit 2 discusses diagenesis and the altering of porosity. Unit 3 explores secondary porosity. And finally, Unit 4 takes a look at the methods used to study porosity and how porosity evolution is applied to hydrocarbon exploration and production. Finally, we'll return for a closer look at the Stirling and Beluga formations up in Alaska. And don't forget, there's a manual which accompanies this program. It covers a wealth of information. Get familiar with it as you can.
In its simplest form, a sand bed is made up of 2 components, the sand grains themselves and the network of pore spaces between them. The volume or porosity of this space is made up of pores and pore throats and is referred to as primary porosity in a freshly deposited sand bed. Permeability is a measure of how well fluids are transmitted through the pore network. The most important factors affecting primary porosity and permeability are textural. They include grain sorting, size, shape, roundness, packing, and grain orientation. Depositional environment, sedimentary structures, and the biogenetic activities after deposition are also often important. There have been numerous laboratory experiments over the years designed to evaluate the relative importance of each of these factors. But the lab work often fails to match the data collected in the field due to the interactivity of various factors and the variables that make each depositional site unique. What is clear, however, is that grain sorting and grain size are the key textural parameters that affect porosity and permeability in uncemented and uncompacted sands. An increase in grain size results in a significant increase in permeability. And although experimental data show that grain size has no effect upon porosity, empirical data often show a modest decrease in porosity with increasing grain size. With an increase in sorting, there is a modest increase in porosity, but sorting doesn't appear to affect permeability. Point bars appear to be an exception to this relationship, however. Their porosities often increase with grain size, and their permeabilities increase with sorting, a fact attributed to unique fluvial processes that produce a loose, propped-open packing style. Sand bodies from various depositional environments are imprinted with well-defined characteristic patterns of permeability variation. Permeabilities in point bar sands are generally higher and more variable than in beaches or dunes, and decrease systematically downstream and towards the banks. Their variability is made clear in this vertical profile through an abandoned Mississippi point bar. This sequence is constructed of 15 units or sediment packages, each separated by thin clay silt layers. The overall permeability of this sand body is controlled to a great extent by these low permeability boundary zones. Beaches have relatively low variability in porosity and permeability, with the variations arranged perpendicular to the length of the beach. Dunes have relatively low variability in porosity and permeability values and show no distinctive trend in permeability variation. Grain shape, roundness, packing, and orientation are less important to porosity and permeability than grain size and sorting, but they undoubtedly have an impact on both. Grain shape is expressed by the degree of sphericity. Roundness refers to the sharpness of the edges or corners of a grain and is not related to grain shape. Sand grains of uniform size and high sphericity and roundness assume a relatively close packing arrangement with moderate porosity. Grains with lower sphericity and roundness pack more loosely due to the bridging of pores, resulting in an increase in porosity and permeability. The effect of packing on porosity and permeability is impossible to isolate from the other textural factors, and so it is undefined. But since it is important in determining the size and geometry of pore spaces, packing nevertheless exercises a fundamental control over permeability. Grain orientation generally has no effect on porosity, but it does have a weak directional effect on permeability. This orientation is often imparted to the grains during the development of sedimentary structures. The structures themselves can also restrict permeability through the development of relatively impermeable bedding plane laminae. These aspects are of prime concern to engineers involved in controlling fluid flow within a reservoir. Shale rip-up clasts are common sedimentary features near the base of channel sequences that, if abundant, can have a significant effect on the porosity and permeability of the enclosing sands. While their microporosity can maintain high overall porosity, they are impermeable and significantly reduce fluid flow through a sandstone. If their presence is not accounted for, there is a danger of overestimating the effective porosity and permeability. The burrowing activity of certain animals, such as crustaceans, bivalves, and worms, can also significantly affect primary porosities and permeabilities. In the course of feeding or hiding, these animals burrow into the sediment, disrupting the sedimentary layers. In many cases, intense burrowing can work so much clay and silt into the sand that permeability drops to zero, but there are also situations where it can improve overall reservoir characteristics by effectively destroying thin, impermeable mud layers.
In terms of a sandstone reservoir's pore system, primary porosity and permeability represent only the starting point of a long evolutionary process. It's a process that is defined by a great number of factors, including, to an important extent, the textural features examined. The results of this process can range between a nearly complete preservation of primary porosity on the one hand to an extensive reorganization of the pore system. But regardless of the outcome, the changes start almost as soon as the sand is deposited. This concludes Unit 1 of GL 505. Consult your manual sections for additional information and be sure to complete the exercises for those sections. The porosity of freshly deposited sands falls in a range between about 30 and 50%. But very soon after burial, a series of diagenetic processes begin that transform these highly porous sediments into less porous rock. With progressively deeper burial, the composition, texture, and porosity of the sand are altered and re-altered in response to changing physical and chemical conditions. The ideal end product is a sandstone in equilibrium with its environment, though in fact subsurface physical and chemical conditions are never truly static. The nature and extent of the porosity modification that has taken place are a function of the original mineralogy, texture, and burial history.
The three mechanisms which work to reduce porosity and permeability are mechanical compaction, chemical compaction, and authigenic cementation. Simple mechanical compaction is the best known and easiest to visualize. It is the result of physical forces that alter a sand during burial and lead to an increase in bulk density as the sand adjusts to the forces of gravity and overburden. As packing of the detrital grains occurs, there is a loss of porosity as well as a reduction in rock volume. Let's look at it in greater detail. Mechanical compaction can take place through grain slippage and rotation, ductile or plastic grain deformation, and brittle grain deformation. During the process of grain slippage, non-deformable grains slip past one another with slight rotation to assume a tighter packing arrangement. The total amount of porosity reduction through grain compaction depends upon many factors. These include such obvious ones as sorting and roundness of the grains, as well as overburden pressure. Studies suggest that common initial porosity losses due to grain slippage and rotation are around 14 or 15%. Grain slippage and rotation occur at depths of 1,500 meters or less, although minor compaction continues down to 2,500 or 3,000 meters. Ductile deformation occurs when grains such as glauconite, fecal pellets, argillaceous rock fragments, and clay clasts are squeezed between and around adjacent rigid grains in response to overburden pressure. Porosity losses, therefore, are heavily dependent on grain composition and vary widely with sandstone type. Glauconite-rich sandstones and sandstones with clay clasts can lose all of their original porosity to ductile deformation, while quartz-rich sands lose very little, if any, porosity in this way. Ductile deformation generally becomes significant at depths greater than 500 meters and continues below 4,000 meters. The third method of mechanical compaction is brittle grain deformation, and it occurs when quartz, feldspar, and shell fragments are fractured or cleaved. Brittle failure of shells and feldspar grains occur at moderate burial depths. Failure of quartz grains tends to occur at greater depths, where framework cement has been dissolved. Depending on the nature of the fracturing, this process can either reduce porosity by promoting a tighter packing arrangement, or it can redistribute porosity by opening new fractures at the expense of existing porosity. Chemical compaction of grains begins when the depth of burial reaches a point where temperature and pressure dissolution reactions begin to occur at grain contacts. The dissolved material then reprecipitates, usually in an adjacent location. The entire process is also commonly referred to as pressure solution. Grain size and shape are key factors. Finer grained sandstones experience more severe pressure solution than more coarsely grained sandstones. Also, highly angular grains, as well as sands with clay coatings, experience more pressure solution than clean, well-rounded grains.
Pressure solution affects a number of minerals, including quartz, calcite, dolomite, chert, and feldspar. For example, chert is more susceptible than quartz, and quartz is more susceptible than feldspar. Determining whether or not a sandstone has been chemically compacted involves a careful examination of grain contacts in thin section and is an important part of any diagenetic study.
In this sample from the Wagon Wheel Formation of the Green River Basin, porosity and rock volume have been lost to mechanical and chemical compaction. Characteristic dissolved grain contacts and reprecipitated quartz, partially filling the remaining pore space in grain structure, provide clear evidence of pressure solution. The dissolution and reprecipitation process typically reduces initial porosities by 6 to 7%. Pressure solution of quartz usually occurs at about 1,000 to 1,500 meters and remains fairly active to depths of 4,000 meters. The third and final diagenetic process is cementation. Which orthogenic minerals will be formed in a sandstone and when is a function of three variables: temperature, pressure, and pore fluid chemistry. As you might expect, there are many possibilities. The most common of these orthogenic cements are silica and carbonates. The principal mechanisms of cementation are recrystallization, replacement or alteration, and precipitation. Recrystallization is a process whereby a mineral or part of a mineral is completely dissolved and reprecipitated in small increments. As the original crystal goes into solution, the successor crystal is precipitated from the same solution, normally as a thin film immediately adjacent to the solid surface. This mechanism is often associated with pressure solution sites. Replacement occurs in much the same way, except that the mineral being dissolved is replaced by a crystal with a different composition. Again, the process takes place in a thin film solution and requires long duration flow of pore water with a suitable chemistry in order to complete the reaction. In this thin section sample, calcite, which has been stained red, has cemented and partially replaced the detrital sand grains. Alteration is a process in which only some components of the original crystal go into solution, leaving behind a crystal with a new chemical structure. In this thin section sample, the original feldspar grains are now nearly completely altered into kaolinite. Nearly all sandstones undergo some degree of cementation, with many losing all primary porosity in this way. These cements can occur as overgrowths and as pore-filling precipitates. Overgrowths occur most commonly on detrital quartz grains. Carbonates such as calcite, dolomite, anchorite, and siderite follow silica as the most common authigenic cements in sandstones. Carbonate cement can form early or late in the burial process, with a porosity-enhancing dissolution phase commonly occurring in between. These events are controlled to a large extent by reactions within shales and mudstones that can supply large amounts of reactive pore fluid to nearby sandstones. The dissolution of shell material is also an important early source of carbonate. Pore fluids originating in the mudstones can also promote the creation of dispersed clays, which generally occur as a pore-filling component and have a variety of crystal sizes and shapes. Because of their microporosity, they don't have much of an effect on the total pore volume of the rock. However, they do produce a variety of adverse effects on rock fluid flow and fluid saturation properties.
Changes in pore fluid chemistry, like those produced during mudstone diagenesis, are just one of the many factors that affect the reduction of porosity and permeability in sandstones. Others include initial composition and texture and temperature and pressure. And it's important to note, as mentioned earlier, that these processes often act in concert with overlapping effects. For example, mechanical compaction and chemical cementation often compete with one another to destroy primary intergranular porosity, particularly in the early stages of diagenesis, with mechanical compaction dominant in the early stages and chemical processes dominant later on.
The original mineral composition and texture of the sand are perhaps the most critical factors governing these porosity-modifying processes. The degree and rate of porosity reduction is directly related to the mineralogical and textural maturity of the sands. Even-grained, quartz-rich sandstones lose porosity relatively slowly by grain rearrangement and by various gradual cementation processes. Poorly sorted sandstones, rich in chemically unstable minerals and rock fragments, undergo a much more rapid and complete porosity loss. Poor sorting makes them very susceptible to mechanical compaction. Their high percentage of unstable materials and rock fragments also makes them further susceptible to chemical reactions that result in pore occlusion by chemical cementation. In some cases, however, small projecting grain edges resist grain rearrangement until overburden pressures increase and they are dissolved by pressure solution. Early carbonate cement can begin forming even before any significant amount of mechanical compaction has taken place. This is particularly true of sands with abundant lithic and volcanic rock fragments, which in addition to calcite may be rapidly cemented with clays and zeolites. These cements can then control or arrest mechanical compaction in sands. When cementation is complete, the sand retains its original open fabric, although no primary porosity is retained, as in this sample taken from 2.6 kilometers in the Picaroon sandstone. Late dissolution reactions may then yield high porosities of secondary origin that mimic the primary intergranular fabric. Unusually high preserved primary porosity at unexpected depths can also occur when early cementation is incomplete, with volumetrically insignificant grain rim cement. This causes little reduction in porosity, yet it lithifies and preserves the original fabric of the sand. However, in sands with abundant soft, ductile grains, most or all porosity may be rapidly lost by mechanical compaction before any significant cementation occurs. Studies suggest that the early introduction of trapped hydrocarbons and the development of overpressuring can stop chemical compaction, authigenic cementation, and possibly even mechanical compaction. This could explain why many deep reservoirs have anomalously high values of primary porosity.
Depending upon the timing of the onset of overpressuring, approximately 2% of primary porosity may be preserved for every 1,000 psi above hydrostatic pressure. However, hydrocarbon generation, which is an important factor in creating overpressures, generally takes place in rocks at or above 90 degrees centigrade. And at this temperature, most primary porosity has already been lost to mechanical compaction and cementation. So what is frequently taken to be preserved primary porosity in overpressured intervals may be, in fact, secondary porosity, the subject of our next unit. This concludes Unit 2 of GO 505. Consult your manual sections for additional information and be sure to complete the exercises for those sections. As we have seen, compaction and cementation generally reduce initial porosities to levels unsuitable for hydrocarbon extraction. But the diagenetic alteration of porosity certainly doesn't end there. The pore systems of sandstones undergo further reorganization during burial in response to changing physical and chemical conditions. These reorganizations can lead to a redistribution of porosity at depth called secondary porosity. Distinguishing between primary and secondary porosity can be tricky and has led to some controversy about how much of the porosity we see is secondary. But nevertheless, it's this secondary porosity that often becomes the reservoir for important hydrocarbon accumulations.
Secondary porosity of diagenetic origin is commonly associated with primary porosity in sandstones from shallow to intermediate depth of burial and low thermal maturity. In sandstones of higher thermal maturity and prolonged burial at depths greater than 2 kilometers, secondary porosity often constitutes the dominant porosity type. However, the development of secondary porosity is neither uniform nor universal. The development of extensive secondary porosity generally requires an open diagenetic system. In closed diagenetic systems, by contrast, neither fluid nor solute moves beyond the reaction cell boundaries, and secondary porosity can only develop at the expense of primary porosity through isochemical dissolution and reprecipitation. Even so, it is still possible for primary porosity to be completely replaced with secondary porosity in this way. In sandstones where dissolution causes a net increase in porosity, solute has to be exported either through escape at the surface or by transfer to another site where it can precipitate. If it is transferred, then the porosity enhancement at one site is linked to the porosity destruction at another location, resulting in a porosity redistribution within the sedimentary basin. The forms of secondary porosity include fracture porosity, shrinkage porosity, and dissolution and replacement. Perhaps the most easily recognized form of secondary porosity is fracture porosity. Caused by tectonic deformation, seismic shock waves, thermal expansion and contraction, along with many other processes, fracturing may be confined to individual grains, intergranular spaces occupied by matrix or authigenic minerals, or can extend across or between several grains. These rock fractures greatly increase permeability and may interconnect pore space that was previously isolated in the unfractured formation, thus enhancing both productivity and hydrocarbon recovery. Dehydration and shrinkage of gels, colloids, and hydrous minerals, and the alteration of organic matter is common in many sandstones and can produce significant amounts of secondary porosity, particularly at burial depths of less than 2 kilometers. However, in the absence of other pore types, shrinkage pores usually form a poorly interconnected network. Dissolution porosity creates the largest volume of secondary porosity by far. It affects both detrital grains and authigenic minerals and can be found to some degree in nearly all sandstones. It is especially prevalent in thermally mature sandstones buried to depths greater than 2 kilometers. It may also form extensively during exposure at unconformities. Partial to complete dissolution of framework grains can significantly enlarge intergranular pores and increase intergranular volume. It also considerably increases pore throat size and therefore permeability. This dissolution can in some instances be so pervasive that the result is an unconsolidated, highly porous sand, as in the Jurassic reservoir sands at the Statfjord field in the North Sea. The dissolution of the interstitial matrix most commonly creates intergranular pore textures. This can increase the effective porosity and vastly improve permeability by removing plugs of matrix material from potential pore throats. In sandstones containing small percentages of dispersed matrix, even minor dissolution can open many pore throats and increase the homogeneity of the reservoir. The dissolution of orthogenic cements and replacement minerals probably account for about 75% of the secondary porosity in sandstones, 50% for cement dissolution, and 25% for replacement dissolution. Carbonates are the most common precursors of both cement dissolution and orthogenic replacement dissolution. As mentioned previously, the dissolution of early carbonate cement is a common explanation for anomalously high porosity at depth, and it tends to produce an intergranular fabric that mimics the primary fabric. However, in many instances, orthogenic minerals cement not only intergranular pores, but replace framework grains and matrix material as well. Subsequent dissolution then removes both cementing and replacement minerals to create pores of composite origin that are larger than those that were originally cemented. Because much of secondary porosity in sandstones closely resembles or precisely mimics primary intergranular porosity, it can easily go unnoticed or significantly underestimated. To make the task a little easier, there are 8 commonly used petrographic criteria for recognizing secondary porosity in thin section. Partial dissolution of grains, matrix, and cement, or replacive minerals can provide conclusive textural evidence for secondary porosity. Molds are dissolution pores conforming in shape to selectively dissolved grains or orthogenic crystals. Pores having characteristic shapes, such as shell fragments, are examples of molds. Inhomogeneity of packing occurs when sandstones of uniform framework grain composition display marked variations of intergranular porosity and packing density. Inhomogeneity can best be seen in thin sections oriented normal to bedding. Pores having significantly larger diameters than adjacent grains provide strong evidence for secondary porosity. These oversized vugs and channels are often the result of dissolution of grains and patches of matrix. Oversized pores adjacent to strongly deformed ductile grains are especially indicative of secondary porosity. Elongate pores can be evidence of secondary porosity if they are significantly more numerous than can be expected from the grain shapes present and the degree of compaction. Grains corroded by direct or indirect in situ dissolution can be good indicators of secondary porosity, as long as the corrosion is sufficiently severe that it eliminates the possibility of predepositional origin or microscopic edge effects. Honeycombed grains resulting from the partial dissolution of feldspar, rock fragments, and micas show many small intergranular pores. These pores give these grains a distinctive texture and render them too fragile to have survived transportation. Open grain fractures form in compacted sandstones where the development of secondary porosity has rendered parts of the grain framework mechanically unstable. Abundantly fractured grains of feldspar, chert, and quartz suggest secondary porosity because these grains are rarely broken during the compaction of primary porosity.
Studying the various types of secondary porosity and what they look like leads to further important questions. How and where is secondary porosity formed? More specifically, what diagenetic processes create it? And what factors contribute to its development? This information, often based in a complex set of geological, geochemical, and hydrological interactions, is critical in order to locate sites of anomalously high porosity and permeability.
The basic framework within which all secondary porosity reactions take place is defined by temperature and pressure. Temperature affects all chemical diagenetic reactions, those that destroy porosity and those that create it. An increase in temperature accelerates the rate of diagenetic reactions, affects mineral stability and solubility, and increases the rate of diffusion. In comparison to temperature, pore fluid pressures in hydrostatic pressure regimes almost always take a subordinate role in the creation of secondary porosity. However, pore fluid pressures in overpressured systems are very important. They favor porosity redistribution and localized strong enhancement of porosity by affecting chemical equilibrium. Elevated pore pressures also limit the destruction of secondary porosity by compaction, permitting the creation and preservation of unusually high porosities during deep burial. A good example is the Venture gas field off the Canadian east coast, which has porosity values in excess of 30% below 4.5 kilometers. Pore fluid chemistry and pore fluid flux are two factors that drive a wide variety of diagenetic processes. As pore water moves along pressure and temperature gradients, it partially equilibrates with different mineral assemblages, alternately acquiring and losing chemical reactants through a continuous series of dissolution and precipitation reactions. These reactions are facilitated by a number of mass transfer processes. Meteoric, non-convective flow systems are driven by gravity and occur in response to differences in elevation between surface recharge and discharge sites. These systems can facilitate the creation of secondary porosity at shallow depths, as acidic groundwater dissolves carbonate and aluminosilicate minerals. But they can also create secondary porosity at considerable depths. Hot springs are good examples of their potential for deep circulation. Beginning at shallow depths, acidic water evolves into low salinity calcium bicarbonate waters. As it travels deeper, it commonly mixes with both subsurface saline formation water and acidic reactants. It is in these zones of mixing that considerable mineral dissolution occurs. Low salinity waters are also involved in a phenomenon known as mixing corrosion, a surprising reaction between low salinity carbonate-saturated pore water and high salinity carbonate-saturated pore water that results in carbonate dissolution. Mixing corrosion causes extensive carbonate dissolution in both shallow sands along coastlines, such as along the Yucatan coast, and in carbonate-rich sandstones buried kilometers deep. Pressure-driven advective flow is responsible for a large part of the secondary dissolution porosity in sandstones, with most of the dissolved material transported for some distance along complex flow paths before being reprecipitated. The pressure gradients are caused mainly by compaction disequilibrium. In subsiding basins with active sedimentation, the flow tends to move reactive waters expelled from fine-grained sediments through the sandstones to shallower, younger zones. Formation fluids can also develop a convective flow due to differences in density caused by local variations in temperature, salinity, or dissolved gas content. Flow across these gradients then has the capacity for large-scale mass transfer and porosity enhancement and redistribution. Dissolved gas convection may be a particularly important mechanism for mass transfer and porosity evolution in geopressured reservoirs. Mass transfer by chemical diffusion is also important, particularly in sandstones with very low or negligible fluid flow. So the development of secondary porosity need not start with high pre-existing porosities. In fact, even dissolution reactions can follow microfractures and a residual microgranular pore system. Of all the factors affecting secondary porosity, the original depositional environment probably has the most broad-reaching impact. It defines the original mineralogy, texture and porosity and permeability. It determines to a large degree the susceptibility of a sandstone to develop secondary porosity in the diagenetic environments that follow burial. Just as with the modification of primary porosity, primary mineralogy and texture also have an important effect on the development of secondary porosity. A primary mineral assemblage rich in coarse-grained quartz sand is unlikely to develop extensive enhanced secondary porosity by grain dissolution. But, because it commonly acquires an early carbonate cement, it is able to resist initial mechanical compaction and is able to develop good dissolution porosity later, resulting in high porosity at unexpected depths. Some of the best secondary porosity develops in sublitheranites and subarcosis, with a dissolution of original feldspar and rock fragments. However, the mineral reactions not only create secondary porosity, they affect changes in pore water chemistry that in turn lead to the redistribution and enhancement of porosity at other sites. Aluminosilicate hydration is a good example. In this simulation, the alteration of volcanic glass to clay produces a characteristic increase in pore fluid pH through the release of hydroxyl ions. Calcium ions are also released. This type of reaction can create strongly alkaline conditions, leading to the dissolution of silica and silicate minerals, while at the same time promoting the precipitation of carbonate-based materials. Highly unstable materials like hornblende, aragonite, and skeletal fragments dissolve under a wide range of pore water chemical conditions, even in the absence of acid or alkaline chemical reactants and without fluid movement. They then commonly reprecipitate in adjacent pores as stable cements, in some cases converting significant amounts of primary porosity into secondary porosity. Secondary porosity in sandstones can also be strongly affected by compaction and chemical reactions in organic-rich shales, evaporites, cherts, and carbonate rocks. During intermediate and deep burial, organic reactions within these sediments release acidic reactants along with large volumes of water that often result in substantial dissolution of detrital and authigenic constituents in nearby sandstones. This thermocatalytic generation of acid reactants and complexing agents for silica and aluminum is probably one of the most important factors in the creation of secondary porosity at depth, generally enhancing and redistributing porosity through substantial dissolution of detrital and authigenic constituents. But how much reactive fluid flows into and through a sandstone depends, to a large extent, on the unit's geometry and structural position. Thin sandstone units interbedded with shales generally have poorly developed secondary porosity, since they are often tightly compacted and cemented. Secondary porosity is much more likely to develop in thicker, laterally extensive, and well-interconnected sandstone units. Structural highs also tend to be sites of greatest fluid flow and secondary porosity development.
With progressive burial, diagenetic factors change. The processes that enhanced or reduced porosity in one area may not be active in another area, and so porosity evolves. This evolution reflects the progressive textural and mineralogical alteration prior to, during, and after effective burial, although burial diagenesis affects sandstones to the greatest extent. It involves a series of interrelated events: the creation and alteration of secondary porosity, the destruction of both primary and secondary porosity, and the progressive changes in mineralogy and texture. Some of the diagenetic changes are reversible, but most leave a permanent textural and mineralogical imprint that then influences how the sandstone responds to subsequent diagenetic processes.
In most sands, diagenetic overprinting of porosity, texture, and mineralogy begins before they are buried even 30 meters. This pre-burial diagenesis commonly reduces porosity by only a few volume percent and produces little, if any, secondary porosity, but it can exert considerable influence on porosity alteration during burial diagenesis. Pre-burial authigenic minerals, especially carbonates and evaporites, can become significant precursors of dissolution porosity during later burial. And as we've mentioned before, early cementation can delay or prevent later compaction. The greatest modifications in porosity at this stage occur in sandstones with a high percentage of labile minerals, such as quartz pore arcosis and litharonites, in which significant redistribution or conversion of porosity can occur. Based on the textural evolution of porosity and grain framework compaction, sandstone burial diagenesis can be divided into 4 progressive stages: immature, semi-mature, mature, and supermature. The following explanation follows the diagenesis of a quartz-rich sandstone. In uncemented sandstones, the immature stage is characterized by primary intergranular porosity. Compaction is essentially mechanical, with little chemical compaction. Secondary porosity through dissolution of grains and pore-filling cements may be well developed and even exceed primary porosity, but total porosity gradually declines with progressive burial. Formation temperatures rarely exceed 60 degrees Celsius. Pervasive chemical compaction marks the end of immature burial diagenesis and is essentially a function of burial time and temperature. The initial and intermediate phases of the semi-mature diagenesis are characterized by a reduction in primary porosity by pervasive chemical compaction and by cementation of quartz overgrowths, as well as carbonate and clay minerals. The development of secondary porosity increases toward the end of the semi-mature stage as a result of the dissolution of a wide range of minerals: carbonate, feldspathic minerals, argillaceous constituents, mica, and silica. But in most sandstone units, average porosity gradually declines while the relative abundance of secondary porosity increases throughout this stage. And significant secondary porosity is usually preserved at the transition to the mature stage, when primary macroporosity disappears in most cases. During the early phases of the mature stage, the dissolution of grain framework and early cements results in the creation or enhancement of secondary porosity. It's at this stage that the creation of secondary porosity is at its peak, because of acids generated in hydrocarbon source rocks with redistribution of secondary porosity resulting in strongly enhanced porosity in many sandstone zones. Most of the sandstone reservoirs of conventional oil and gas are found in the mature zone. On average, secondary porosity declines in the mature zone until effective porosity is obliterated due to mechanical and chemical compaction as the supermature stage is reached. An exception occurs where the chemical dehydration of shales produces large volumes of pore fluid that contribute to the formation of geopressures and delays the destruction of porosity. In the supermature stage, any significant secondary porosity that forms is temporary and is quickly eliminated by cementation or compaction. Some fracture porosity does exist, and in some circumstances, gas-filled reservoirs inherited from the mature stage are preserved. In most cases, these same main diagenetic stages can be identified in quartz-poor sandstones. However, the zones are not as clearly defined. And in contrast to quartz-rich sandstones, quartz-poor arcosis and litharonites tend to lose porosity at shallower depths and at lower temperatures, as ductile and brittle compaction play a greater role and mineral orthogenesis is more pervasive. The development of good secondary porosity is also less common during deep burial.
Just how is porosity studied? Well, of all the factors that affect porosity development, mineralogy, temperature, and pressure, for example, structure and sandstone geometry can be mapped and evaluated using standard methods.
The techniques fall into two categories. First, techniques that are used to describe the nature of the porosity, its interconnections, and its response to different types of fluids. And second, techniques that attempt to interpret and model the diagenetic history of the rock in order to develop porosity prediction models. The first set of techniques begins by study of the rocks themselves. Samples from cores, cuttings, and on occasion outcrops are valuable sources of direct reservoir rock information, and they are analyzed in a number of ways. Light microscopy, or thin section analysis, is used for quick and reasonably accurate estimates of volumetric abundance of the pores and rock composition. Ultraviolet fluorescence is used to study the zonation of carbonate cements and in timing different phases of hydrocarbon migration. Scanning electron microscopy provides information about clay types and structures and about pore form and distribution. X-ray diffraction is used as another means of checking the overall composition of the rock. Pore casts, made by injecting a colored plastic resin into the pore system and then dissolving the sandstone with hydrofluoric acid, provide valuable information on the pore geometry and size distribution. Mercury injection curves are generated by injecting mercury into the rock's pore system and plotting the volume of mercury injected as a function of pressure. This test provides the size range of a sandstone's pore throats and is useful in reservoir analysis. Other important analytical techniques involve downhole wireline logging. In sonic logs, porosity is indicated by variations in sonic travel time. In density logs, it is measured by variations in rock bulk density, and in neutron logs by changes in hydrogen ion concentration.
To determine the history of porosity development in a target sandstone, the data from these studies can then be taken further with a thorough petrographic study, an analysis of porosity versus depth plots, and with detailed pore fluid geochemistry. However, in interpreting porosity data, we must also consider the unique reservoir properties of secondary porosities and orthogenic clays.
Petrophysically, sandstones with secondary porosity are considerably different from similar lithologies with primary porosity. Irreducible water saturation in gas-bearing sandstones with secondary porosity is often much lower than gas reservoir sandstones with primary porosity. They also have better welded grain contacts and greater mechanical competence, a feature that manifests as reduced sonic travel times when compared to sandstones with comparable primary porosity, and results in a tendency toward fewer sand production problems. In fact, the variability of pore sizes, pore types, and hydrocarbon recovery characteristics of sandstones with secondary porosity is more similar to that found in carbonate rocks. Dispersed orthogenic clays can have a negative impact on permeability that far outweighs their volumetric contribution. For example, their high microporosity can result in high log-derived porosity values, while effective porosity is actually very low. They can also create permeability-choking chemical reactions with drilling fluids, or become dislodged by high fluid flow rates and rapidly constrict the pore network. So, in defining the reservoir potential of a sandstone, a correct identification of the percentage of detrital clays that are not part of the pore network from the percentage of dispersed clays that are is essential. With an understanding of the characteristic signatures of primary and secondary porosity, and with a complete set of porosity data, it is now possible to employ porosity prediction techniques. There are two approaches to porosity prediction: the empirical approach and the modeling approach. The empirical approach consists of observing variations in sandstone porosity with increasing burial depth, based upon data from other wells in the area, and then applying this information to predict porosities in undrilled plays. It can be a particularly effective technique in sandstones of uniform lithology and diagenesis, but locally important cementation or dissolution can reduce its effectiveness. Chemical and mathematical modeling use sophisticated computer programs for geochemical modeling of water-rock interactions. They are specifically designed to simulate diagenetic sequences and provide predictions on cementation and dissolution. This type of modeling is particularly useful in identifying the processes that control porosity evolution, as an aid in developing play concepts.
It's important to remember that the success of any predictive technique depends on the quality of the information it is based on and on an informed interpretation. That requires carefully executed analytical procedures and data analysis, and it requires that you know as much as you can about the complexities of the depositional and post-depositional factors that affect porosity development. We'll now review some of these factors as we return to the Stirling and Beluga formations for a more detailed look.
As we mentioned earlier, the Stirling and Beluga are interfingering fluvial sandstones and shales. And even though they were deposited in a similar environment and have a similar burial history, the Stirling has excellent porosity and reservoir characteristics, and the Beluga has very poor porosity and reservoir characteristics. The porosity evolution of these sandstones is an excellent sample of how depositional grain composition influences destruction of primary porosity and generation of secondary porosity. Both the Stirling and the Beluga contain quartz-poor sandstones. The Beluga sandstones are poorly sorted argillaceous litharonites, consisting mainly of rock fragments of fine-grained slate and metagraywacke. The Stirling sandstones are well-sorted, fine-grained volcanic litharonites, consisting of volcanic rock fragments, quartz, plagioclase, biotite, and mafic minerals. These sediments were deposited in a non-marine four-arc basin that received more than 5,000 meters of tertiary clastics. The Beluga Formation has a low sand-shale ratio and discontinuous sandstone units up to 3 meters thick, which were deposited in braided streams. The Stirling Formation was deposited in meandering streams and rivers, and is characterized by a high sand-shale ratio and sandstone units up to 15 meters thick. Maximum paleoburial depth for both ranges from 2 to 3 kilometers, but their diagenetic pathways were radically different. Along with slate and metagraywacke sand grains, the Beluga also contains detrital clay and silt matrix, so the percentage of ductile grains is extremely high. And early ductile compaction destroyed most of the primary intergranular porosity. Development of secondary porosity was restricted to the leaching of scattered altered biotite. Pore water became stagnant, except when shale dewatering or gas generation from the plentifully dispersed carbonaceous material and intercalated coals caused overpressures and opened fractures. The Stirling sandstones also lost most of their primary porosity to mechanical and chemical compaction. But in contrast to the Beluga, diagenetic alteration didn't stop there. The Stirling sandstones contained a much higher percentage of chemically labile and mechanically rigid grains, and the sand layers were much better interconnected, facilitating pore fluid flux. So it is likely that migrating groundwater and gravity-driven fluid flow caused the dissolution of the labile grains, creating some early secondary porosity, and at the same time mechanical and chemical compaction was occurring. Later, more extensive dissolution of framework grains occurred and created most of the present 25 to 40% porosities. This dissolution preferentially removed volcanic glass, altered biotite, and altered hornblende, and in the process eliminated about 30 to 40% of the original sand. It also significantly increased the relative amount of rigid and chemically stable grains. Subsequent grain framework collapse occurred in some sandstones, moderately reducing secondary porosity. But most of the Stirling secondary porosity is intergranular and well connected by enlarged pore throats. Differences in sand composition, sandstone geometry, and possibly clay mineralogy of intercalated shales greatly influence the porosity of the Beluga and Stirling sandstones. The Stirling's thick point bar sand units were flushed by acidic pore water after compaction of primary porosity and produced excellent secondary porosity and permeability. The Beluga, on the other hand, contained little highly soluble material and had abundant ductile grains. These sands also occurred in thin discontinuous lenses that were incapable of transporting sufficient volumes of pore water for dissolution to occur.
This concludes GL 505, Porosity Evolution of Sandstone Reservoirs. Our goal was to introduce you to the dynamic and complex relationships that lead to the reduction and reintroduction of porosity in the subsurface. As you've seen, the processes and the factors that influence what happens to porosity with burial are many and interactive. Understanding what they are and how they operate is the key to the important task of developing effective porosity predictions for exploration and production. Remember, the topics we've just completed discussing are covered in greater detail in the manual. Also, don't forget to do the exercises related to those topics. We'll see you in the next video.